Oh, good afternoon, Physics 30s. Mr. Thompson here. Finally, a little video visual. Looking at Unit 5 on atomic theory. All right, well, here's a little illustration comic for you. Haha, laugh, laugh. Anyways, we're looking at quantum nature of EMR. Let's look at lesson one on photon theory. So it says up to the end of the 19th century, EMR was viewed as a wave, which was confirmed by its many observed properties like refraction, diffraction, interference, polarization. However, in the early 20th century, the certain experiments dealing with light, as we will soon see, could only be explained by viewing EMR as composed of tiny particles of energy, which we term photons. Scientists came to realize that EMR has both wave and particle properties, which is called wave-particle duality. Put it this way, a complete picture of light doesn't just involve the wave idea or the particle idea separately, but together. Because some experiments exhibit the wave nature of light or demonstrate the wave nature of light, and some experiments demonstrate the particle nature of light. So, what we're doing is we're studying the particle nature of light, and this corresponds with chapter 14 of the textbook. All right, energy of a photon. According to photon theory, EMR is composed of bundles, quanta of energy. The energy of a photon is calculated with E equals hf, where E is energy, F is frequency in hertz, and H is Planck's constant, 6.63 E negative 34 joules times seconds. Or we'd say joule seconds. Further, right, if you use the universal wave equation, right, V equals F lambda, well, we can substitute in for frequency C over lambda. And so you get E equals hc over lambda. Of course, these two formulas are on your data sheet. Check it out. Wavelength is in meters. Note, high-frequency EMR, such as UV, X-ray, gamma, right, has the highest energy photons. This is why it is more likely to do damage to human cells or the DNA, the genetic material of the cell. Since the photon energies are so small, they're often measured in a different unit now. It's the electron volt. Lowercase e, capital V, it's equal to 1.60 times 10 to the negative 19 joules, which corresponds with the elementary charge, but it's not a charge, it's an amount of energy. All right, intensity, brightness of EMR. Intensity is the energy of EMR. So the classical wave theory thinks that the bright EMR has a high amplitude, a high energy, and a dim EMR has a low amplitude or low energy. But quantum theory is different, right? Intensity is really, it's supposed to be the number of photons. So intensity is kind of like bright light. You think about it, right? A lot of photons are coming out of the light source. And low intensity, which means essentially dim EMR, less photons. So instead of in terms of energy or amplitude, we think about the number of photons. And that's what the quantum theory is about. It's why it's very different than the classical theory. What do we accept? Quantum theory. E total, though, is of course the number of photons times the energy of each photon. Makes sense. All right, let's take a look at some example problems to get ourselves going. Okay,